In this video we're going to be looking at covalent structure. Now there's two types of covalent structure, but we'll only look at one in this video. There are giant covalent structure and simple molecular structures. Giant covalent are things like diamond and graphite. We will not be looking at them in this video, but we're going to deal mainly with simple molecular structure. That is the structure of molecules. Most of the compounds that we deal with, certainly to do with organic chemistry and chemistry of molecules within the air and our living systems, are molecules, so this is quite important. I'm going to introduce a new concept based on a previous video on electronegativity. Now this concept is called intermolecular forces. That is the forces that exist between molecules, and there's three types which I'll just introduce you to now. So intermolecular forces, inter meaning in between, molecular meaning molecules. Okay, so we're dealing with the forces that exist between molecules. Now, these have to do with the covalent bonds that are in the molecule itself, i.e. whether the bonds are non-polar covalent or polar covalent. To understand a bit more about that, have a look at the electronegativity video. I'm now going to look at the three types of forces individually. So the first type of force is a van der Waals force. Now, that's named after the Dutch scientist Johannes Diederik van der Waal. And these particular forces apply to molecules which have non-polar covalent bonds, but also to molecules that are symmetrical, even if they contain polar bonds. So, when I'm going to describe this, I'm going to look at hydrogen molecules. So, I'm just going to draw out a hydrogen molecule, two of them in effect, and we're going to talk about the interactions that exist between the molecules. We know that there are two hydrogen atoms on either side of this covalent bond. Therefore, they have the same electronegativity, so the electrons themselves tend to move randomly between the two atoms, i.e. they fluctuate between the two atoms. So that electron density, that cloud of electron density, just constantly fluctuates or moves. As this moves, at any one point in time, it will be at one end of the molecule. So let's say, for example, the electron density is shifted over to this hydrogen atom on the right hand side here. Then this hydrogen atom will have an instantaneous partial charge of delta minus, while this one will be delta plus, thus creating an instantaneous dipole. For more on that, see the electronegativity video. As this specific hydrogen molecule H2 comes closer to another molecule, that partially negative hydrogen atom will induce, or that side of the molecule will induce, a dipole in a neighboring molecule. So as that comes closer, suddenly the electron density that's fluctuating between these two hydrogen atoms starts to shift closer to this hydrogen atom, resulting in a partial negative here and a partial positive charge. What that means is we then will get a partial attraction between one side of this molecule and this side of a neighboring molecule, because we've got a partially negative charge here which is attracted to a partially positive charge here. Remember that this is van der Waals that we're talking about, okay, system 1. And just to describe, these are clouds of electron density. So if I had a cloud of electron density here that was partially negative, partially positive here, as that comes closer and closer to another molecule, the electron density in the neighboring molecule will start to shift closer and closer to the further atom, resulting in a partially positive charge here, and this one being partially negative. And that's a van der Waals force. It's this interaction between neighboring molecules by an induced dipole. Here, it's this interaction here. Now, that's a simple hydrogen molecule. As the number of electrons increase in a molecule, then so do the strength of the van der Waals. Also, if you're thinking about an organic molecule and a long chain organic molecule, the more bonds there are,
then the bigger the molecule, then the more points of contact between molecules that have non-polar covalent bonds, then the stronger the overall van der Waals force of attraction. What does this mean? Basically, if we have a stronger van der Waals force of attraction, then we essentially have a higher boiling point. Reason being that the boiling point is the point at which the molecule will convert from a liquid to a gas. You have to break the intermolecular forces to do that. If the forces are stronger, then the molecule itself will have a higher boiling point. The next intermolecular force we'll talk about is dipole-dipole interactions. For this one, I'm going to draw out a hydrogen chloride molecule. So we know that because the electronegativity of chlorine is quite high, this has a permanent dipole within the molecule, i.e. there's a partially negative chlorine atom and a partially positive hydrogen atom. For more on that, see the electronegativity video. So there is a permanent dipole within the molecule. That is a molecule which has a permanent charge across a covalent bond. Remember, that's just a partial charge. So if I want to talk about the forces between two molecules of hydrogen chloride that have a permanent dipole, that is, they have permanent partial charge, then it's fairly straightforward that the interaction there will be between the partially negative chlorine and the partially positive hydrogen atom. That interaction there is the dipole-dipole interaction. So just to write that out, it's that interaction which is the dipole-dipole. And from above, this is the van der Waals force of attraction there. Now, dipole-dipole interactions tend to be much stronger than van der Waals' force of attraction. Reason being is that there's a permanent partial charge on the molecule and therefore a permanent energetically favorable interaction between molecules. The last one I'm going to talk about is hydrogen bonding, which is by far the most important. Reason being is that because it's the intermolecular force that keeps us alive. Because at room temperature, water should really be a gas, but in actual fact it's a liquid, which we're very, very thankful for. So we're going to look at a water molecule and its neighbouring water molecule here, and talk about the forces between those two molecules. Let's draw in the partial charges. We know that oxygen will be negative, partially positive hydrogen, partially positive hydrogen, partially negative oxygen there. Okay, I'm going to draw in the lone pair on my oxygen atom. Okay, because with hydrogen bonding, there's a strong dipole-dipole interaction between an electron deficient hydrogen, that's a hydrogen which has its electron density removed, in one molecule, and the lone pair of electrons on a highly electronegative atom in a different molecule. Now, that highly electronegative atom is either going to be an oxygen, a nitrogen, or a fluorine. So in this case, it's just the oxygen. So the force of attraction that exists here is the one between that partially positive hydrogen atom and the lone pair of electrons in this oxygen atom, and that is called a hydrogen bond, and that is by far the strongest of the intermolecular forces. So that will also happen between molecules containing nitrogen and hydrogen, so right there, and that will also happen between molecules of hydrogen bonded to fluorine. The reason being the nitrogen, oxygen and fluorine are electronegative enough to cause this hydrogen atom and this hydrogen atom to be suitably electron deficient, therefore resulting in a very, very strong interaction. Okay, so that will give us our highest boiling point. So in order of strength then we have van der Waals being the weakest, we have dipole, dipole in between, and then we have hydrogen bonding being the strongest.